This video is about diagonalizing matrices, or diagonalization for short. We only have two objectives. We're going to define similar matrices and diagonalizable matrices, and then we're going to learn how to diagonalize matrices. We'll start with a definition of similar matrices. We'll say if A and B are square n by n matrices, and if P is an invertible n by n matrix, and if A can be factored as P times B times P inverse, then A and B are similar. This is a specific use of the word similar. In everyday English, matrices A and B might be similar if they have something in common. Maybe if they're the same size, or if they both have only real number entries, or some other subjective similarity between the two. But in linear algebra, similar means one thing and one thing only, and it means this. A and B are similar if A is equal to P inverse for some invertible matrix P. Our first theorem says that similar matrices have the same eigenvalues. This is a non-obvious and interesting and useful fact. If A and B are similar, meaning this equation is satisfied, then they have the same characteristic polynomial and therefore the same eigenvalues. Before we look at the proof of that theorem, I just want to point out that if A is similar to B, then B is also similar to A. In other words, if A is equal to P inverse, well, we could multiply both sides of this equation on the left by P inverse, and then again on the right by P. P inverse times P is the identity, and P inverse P here is also the identity. And so we end up with B equals P inverse AP. And then if we let Q equal P inverse, I can write B equals QA Q inverse, and Q is an invertible n by n matrix, and therefore we could say B is similar to A. So in our definition of similar matrices here, we can say that A and B are similar. A is similar to B, and B is similar to A. Okay, the proof of this first theorem is very straightforward and just relies on the definition of similar matrices and the properties of determinants. If we replace A with P inverse, since one of the conditions of the theorem is that A and B are similar, therefore we know that this matrix P exists such that A is equal to P inverse. I'll replace A here with P inverse, and then I won't go through every single step here, but we're just using properties of determinants and matrix multiplication here to show that the determinant of A minus lambda I is equal to the determinant of B minus lambda I. And remember that the determinant of A minus lambda I is just the characteristic polynomial of A, and likewise the determinant of B minus lambda I is the characteristic polynomial of B, and that proves the theorem. Next, we'll say that an n by n matrix A is diagonalizable if it is similar to a diagonal matrix D. In other words, A is equal to P inverse, where P is an invertible n by n matrix and D is diagonal. Remember the definition of a diagonal matrix. If D is a diagonal matrix, the main diagonal entries can be any numbers, D11, D22, down to DNN, and the lower triangle is all zeros, and the upper triangle is also all zeros. Some or all of these diagonal entries may also be zero, but they don't have to be. Also notice that only square matrices, n by n matrices, can be diagonal. Then we have the main theorem of this section, the diagonalization theorem. It says that an n by n matrix A is diagonalizable. In other words, it satisfies this definition. It's similar to a diagonal matrix if and only if there is a set of n linearly independent eigenvectors of A. Furthermore, if A is diagonalizable as A equals P inverse, the columns of P are these n linearly independent eigenvectors of A, and the diagonal entries of D are the corresponding eigenvalues of A. The proof of this theorem is in the book. It's pretty long and involved, so I'm going to skip it for the sake of time here. The important thing is this second sentence, starting with furthermore. This tells us actually how to find these matrices P and D. Here's another theorem that makes things a little bit easier. It says that an n by n matrix A is diagonalizable if it has n distinct eigenvalues. The proof of this one is very simple. Since A has distinct eigenvalues, here by the condition, the set containing an eigenvector corresponding to each eigenvalue is linearly independent. By the diagonalization theorem, then, A is therefore diagonalizable. And this part we saw in the previous lecture on eigenvalues and eigenvectors. There's a theorem that says distinct eigenvalues correspond to linearly independent eigenvectors. Okay, let's do an example. We saw this matrix in the previous lecture when we found the eigenvalues and eigenvectors for this matrix A. We found the eigenvalues to be -1 and 4 with these bases. So this was a basis for the eigenspace corresponding to -1, and this set is a basis for the eigenspace corresponding to 4. Well, the diagonalization theorem tells us how to diagonalize this matrix A. In particular, we know that A is diagonalizable because it has distinct eigenvalues. Otherwise, we could check to see if we put these two vectors in a set that they formed a linearly independent set, which they would, but it's easier just to look at the eigenvalues. If the eigenvalues are distinct, then A is diagonalizable. If we come back and look at this theorem again briefly, notice that this is not an if and only if statement. It's just an if statement. So it's not a bidirectional implication, it's a one-way implication. In other words, if A has n distinct eigenvalues, then A is diagonalizable. The converse is not necessarily true. If A is diagonalizable, it is not necessarily the case that A has n distinct eigenvalues. It may not. What does that mean in practice? Well, if we found that there were, say, 3 eigenvalues and 4 had a multiplicity of 2, in other words, the eigenvalues were -1, 4, and 4, then there would be 3 non-distinct eigenvalues, and this theorem wouldn't apply. But that doesn't mean that A would not be diagonalizable. Maybe it would, maybe it wouldn't. We would have to use some other theorem to figure that out. Okay, so back to the example. The diagonalization theorem tells us how to diagonalize A, which means find this matrix P and find the matrix D. Notice when we say that A can be diagonalized as PDP inverse, we are not turning A into a diagonal matrix. Here's A back up here. This is not a diagonal matrix, and we're not going to change it into one somehow. The word diagonalize may suggest that that's what we're doing, sort of like row reducing. We're going to do something to A and turn it into something else that is a diagonal matrix. That's not what we do when we diagonalize A. When we diagonalize a matrix, you can really think of it as factoring. We're going to factor A as P times D times P inverse, where D is a diagonal matrix. So in practice, when you diagonalize a matrix, really what you're doing is you're finding P and you're finding D. And the diagonalization theorem tells us how to do that. We simply take the vectors that are in the basis for the eigenspaces and make those the columns of P, and then put the corresponding eigenvalues in the diagonal matrix. Now we have to be a little bit careful. Since -1, 1 is an eigenvector corresponding to -1, if I put -1, 1 as the first column, -1 has to be the first eigenvalue in D. And then 2, 3 is the second column, and so its eigenvalue 4 is the second eigenvalue on the diagonal. An equally correct answer here would be to put 2, 3 first, and the eigenvalue 4 first in D, and then -1, 1, and then -1 as the second eigenvalue on the diagonal of D. So there are 2 possible correct answers here. Normally, we don't compute P inverse, since that's a trivial thing to do on a calculator or a computer. If we have P and we know that P is invertible, we can compute P inverse if we need it. But when we diagonalize a matrix, we generally just give P and D. Since we generally don't calculate P inverse, if you want to check your answer, you can take the equation A equals PDP inverse, multiply by P on the right on both sides. P inverse P cancels to the identity, and we have the equation AP equals PD. So you can just multiply A times P and then multiply P times D, and if they're equal, then you did the diagonalization correctly. If they're not equal, well, then you made a mistake somewhere. In this case, here's AP, A times P, and we get this matrix. Then when we multiply P times D, here's P and D. Interestingly, we get the same matrix as up here. So AP is equal to PD, and we have a correct factorization or diagonalization of A. Okay, this next theorem is really useful. This is, in practice, the main theorem that we use to decide whether matrices are diagonalizable. Remember, before I said if the eigenvalues are not distinct, then we have to use some other way to figure out if the matrix is diagonalizable. Well, this is that way. This theorem says if A is an n by n matrix, it's diagonalizable if and only if the geometric multiplicity for lambda is equal to the algebraic multiplicity for lambda for every eigenvalue lambda of A. So we can summarize that by saying diagonalizable means equal multiplicities, or simply diagonalizable matrices have equal multiplicities, meaning the geometric and algebraic multiplicities are equal for every eigenvalue. And the nice thing is this is a double implication, meaning if this is true, then A is diagonalizable, and if A is diagonalizable, then this is true. So we just have to check to see if the multiplicities are equal for every eigenvalue. If they are, we know the matrix is diagonalizable, and if they're not, we know the matrix is not diagonalizable. So when we have an example like this, diagonalize A if possible, well, if we get distinct eigenvalues, then we know it's possible. But if we don't, we are going to solve for the eigenvalues in the eigenspaces anyway in order to use the diagonalization theorem to diagonalize A. And while we do it, we'll be able to observe the algebraic multiplicity and the geometric multiplicity of each of the eigenvalues. So we'll figure it out along the way. In practice, when we're asked to diagonalize a matrix if possible, we don't really worry about the if possible part. We just start diagonalizing it. And if along the way it turns out that it's not possible, we'll find that out. Okay, so if we go back to this example, we did this example in a previous lecture as well on eigenvalues and eigenvectors, and we found that A had eigenvalues 4 and -2, and -2 had an algebraic multiplicity of 2. And the eigenspaces had these bases. This is the basis for the eigenvalue 4, and this is the basis for the eigenvalue -2. And here we can see whether this is satisfied or not just by observation. We saw that the algebraic multiplicity of -2 is 2, and the dimension of the eigenspace for the eigenvalue -2, which is the geometric multiplicity, is also 2 because there are 2 vectors in the basis. We can summarize that here. The algebraic multiplicity of 4 is 1. The geometric multiplicity of 4 is also 1. The algebraic multiplicity of -2 is 2. The geometric multiplicity of -2 is 2. And since these multiplicities are equal and these multiplicities are equal to each other, that satisfies the condition here for this theorem, and therefore we know that A is diagonalizable. Therefore, we can construct P and D as usual. We're going to take the basis vectors for the eigenspaces, put those into a matrix, and we're going to call that P. Then we're going to construct a diagonal matrix, D, with the corresponding eigenvalues on the diagonal. So this basis vector corresponds to the eigenvalue 4. It's the first column, so 4 is the first eigenvalue. These two correspond to the eigenvalue -2, so I'm going to have -2's in both of these diagonal entries. If you think about it, you'll notice that I could exchange the position of these two columns since they're both in the same eigenspace, and these numbers would not change. They would both still be -2. Likewise, I could rearrange the order of these. I could swap these two and say 1, 1, 0, 1, 1, 2, and then exchange the position of these two eigenvalues and say -2, 4, -2, and that would be another correct answer. So with larger matrices, there are many possible correct diagonalizations, depending on the order that you put the basis vectors into P. The important thing is you just have to make sure that the eigenvalues match the corresponding basis vectors. All right, that concludes this relatively short video on diagonalization. We defined similar and diagonalizable matrices, and then we saw some examples of how do you do that? How do you diagonalize a matrix?